Again, welcome to this amazing event, and thank you for joining us. And I'm going to hand over to Professor Roger Clay, and I'll just make him host. And thank you very much, Roger, for joining us for this event. And I'm going to pin your profile now. And over to you, Roger.
Okay. Should something be happening, Matt?
Oh yes, sorry. Yeah, feel free to just to give a brief introduction to yourself, and then if you like, you can
Okay.
share your screen if you'd like.
Okay, fine, thanks. Yeah, I'm Roger Clay. I'm at the University of Adelaide. For my sins, I've been here since 1971, so you might guess that I'm retired, which is where the emeritus bit comes in front of the professor bit. Um, I I'm a physicist, but really what I moved into was astrophysics, and the bit of astrophysics that I particularly been in has been what used to be called cosmic ray physics. Now we call it fancier things, but essentially the thing that's happened in astronomy and astrophysics over the last 40 or 50 years is that we've got all sorts of different new sorts of astrophysics. So we tend to call ourselves multi-messenger astrophysicists. Uh, so so I do high energy particles. The guy in the office next to me studies neutrinos from the cosmos. The guy in the next office down studies gamma rays from the cosmos. And I've done all of those things. The only part of astrophysics I've never done is optical astronomy, which is just a bit odd, but that's how it is. Um, but all those different forms of astrophysics, we all have different techniques, and those techniques are unique to all of us. And the thing that I've ended up being associated with most has been hardware for detecting particles, and the particles that we detect mainly by accident are these things called muons. So I'm going to talk to you about muons for the next half hour, 35 minutes or so. Uh, my research groupings that I'm in are two. One is that I study low energy cosmic ray particles. That is that I study particles that are coming through the heliosphere. That's the region around the sun. But I also, I've been for the last 30 years or so, a member of what's called the Pierre Auger collaboration, where we detect the most energetic particles in the universe. Those are particles that where an individual nucleus has got as much energy as a tennis ball played by a superb tennis player, like 50 to 100 joules of energy in a single tiny particle. We don't know where nature produces these things, and so we're trying to find that out. But today I'm going to talk about muons, so I want to do a couple of things before I show you the slides, okay? Uh, so I got into this business around 1970, and I'd been worked in the radio field, and I was a postdoc, and I was told by my boss to calibrate some radiation detectors, and he said, measure the muons through these things, and I said, what? It was that was a bit of a shock, and so I learned some things about muons, but I also learned that there wasn't a book that told you how to use muons. It was a bit like when we first had the big mainframe computers. We went along and used the computers, and you did it by word of mouth. Nobody had written down a manual that said you go to an IBM 7090 and this is how you make it work. You talk to your mate and he gave you a few cards and that was it. So I've learned something about muons over the period of time. So Matt, you can see me okay here, I guess? Yep, good. Uh, so uh, Before we get on to other things about muons, the usual way that we have for detecting muons is with a piece of plastic that has a chemical in it that scintillates. and the piece of plastic might look like that. Okay, that's just a 10 millimeter thick piece of plastic, which is loaded with scintillating material. When a particle goes through there, a charged particle goes through there, that charged particle produces a little bit of scintillator light, usually in about a nanosecond or two, 10 to the minus 9 of a second, pretty fast. And then our task is to pick up that light from the scintillator. Now, if I just have a bit of scintillator like that, and I just have it sitting horizontally, then particles will go through there that originated with cosmic rays that have been wandering around our galaxy for 1 million years. And those particles, when they get to here, are typically muons. And there's 1 per square centimeter per minute that goes through this. And they're going through it all the time. And so it's the background radiation that you get when you're not in a radioactive environment. These muons are always there, around 100 a second going through your body at the moment. Doesn't hurt, and hopefully doesn't produce anything very bad, not like alpha particles or something. Okay, so you get a little bit of light from one of these, and you've got to pick out that light. Now, there's an old-fashioned version of plastic scintillator, which is called sodium iodide, and that's a sodium iodide scintillator. Does exactly the same thing, except that this thing, which you might find in a school lab in a drawer somewhere, has got iodine in it, and iodine's a fairly heavy nucleus, and so gamma rays will interact with that. So this is good for gamma rays, whereas the plastic is good for just any old thing that goes through, and it's cheap. This thing costs you $1,000. That costs you a lot less. Okay, so you pick up the light, and you pick up the light with a photomultiplier. That's a photomultiplier. Or if you want to pick up a lot of light, use a big photomultiplier. Okay, this is just a photoelectric cell. It's got a photoelectric surface on the front, and it's got fancy electronics inside that means you get a measurable signal out the back end of it. Okay, so those are the tools of the trade. And so I should, I'll, in a few minutes, I'll talk to you about a thing that Swinburne Uni produces called EduMOD, which uses plastic scintillators, but it's uses a more modern version of a photomultiplier called a silicon photomultiplier. It's a little bit like an array of very, very tiny Geiger counters. A little bit different. This is analog. The silicon photomultiplier is more suitable for digital things. So far, so good. Okay, I'm going to start my talk. All right, okay, so I'm going to attempt to share this screen. Okay, am I doing good? Is that okay? Yeah, okay. So I'm going to talk about muons, and I'm going to talk about how we detect them, and a little bit about some of the things that people have done in the past with muons, and then we'll see how far we get. So I mentioned that these cosmic ray particles come from outer space somewhere. So this is a little diagram of particles that have come from outer space, might have traveled, as I said, maybe 1 million years wandering around our galaxy. And they interact with this very thin film around our Earth called the atmosphere, with a particle interaction. And that produces a cascade of secondary particles. And some of those are muons. And so when we detect a muon, effectively we've measured something about the original cosmic ray. That's the name of the game. So the muons wander down through the Earth's atmosphere, and we detect them, as I said, 1 per square centimeter per minute, pretty well everywhere. But these things have come through the atmosphere. So if you go up in an aircraft, you get a lot more of them. And if you go a little bit higher than a normal intercontinental aircraft, say 50,000 feet, 60,000 feet, something like that, in these weird old-fashioned units, then that's where the radiation is highest. And so you can talk to your students about radiation dosage and the like, and you can talk about people flying in aircraft who are the people who have the biggest radiation dosages here on Earth. And so it's really sounds like a good job to be in a cabin crew of an aircraft or a pilot. But in fact, they're the people who have the biggest radiation doses for any job that there is. Okay. I just thought I'd scare you with that. That's okay. All right. And I would really like it if I could. There we go. Okay. So, muons were first discovered in the 1930s, and people were measuring particles with ionization chambers or cloud chambers, and they saw interactions of particles. A particle would come in, and I'll show you a picture in a minute, and you get many particles coming out. And so the stuff that was coming out, you say to yourself, well, where's that come from? And the answer seemed to be that was coming from particles that were built in to the nucleus in the first place. But of course, Einstein had told us that E equals mc squared, which means that you can always trade the energy that you've got from this initial cosmic ray for an amount of mass. And so these interactions were producing mass from the original energy. And the question then is, what sort of particles are they? And it was assumed at first that they were the particles that sort of held the nucleons together, the protons and the neutrons that we know are in a nucleus, whatever that may mean. I mean, in a nucleus is the way we hand wave it, but it's not really like that. It's quantum numbers and the like. So what comes out are these things that was assumed to be the glue that held the nucleus together, which we now call pions. And indeed, the pions are there, but the things that are detected mainly are the muons, because the pions only last for a very short time, as we'll see in a moment. So what you got is a particle that comes in. It's been wandering around the galaxy for a long time. It's got a lot of energy, interacts with the nucleus in our atmosphere, and stuff comes out. And that stuff is produced with the right quantum numbers, otherwise you get the wrong stuff, but the mass of it has come from the energy of the initial particle. Okay, so here's a picture that was made by my boss when I first came here. It's a cloud chamber picture. And what's happened here is the particle that has come into the cloud chamber from the sort of top leftish region, and it's interacted in this case with some of the material in the edge of the cloud chamber, and it's produced a cascade of particles. Now, actually, these are all charged particles, otherwise you wouldn't be able to see them in a cloud chamber, but there's lots and lots of them. And some of these are pions, but the pions will decay very quickly to become muons and neutrinos, which won't show up here, and all sorts of oddball things as well. So if you were to go to CERN in Geneva, where there's the Large Hadron Collider, basically these are the sort of things that the LHC will be measuring. And then the LHC would then try to measure each of these individual secondary particles to figure out what happened in the initial interaction. Okay, so many of those are pions, and the process is that pions are produced in the initial interaction, and after a little while, it says here 26 nanoseconds on an average, they'll decay, and you'll get muons, the mu plus and the mu minus, and some neutrinos, the nu with a mu stuck on there, and those muons, after a while, in my terms, an awful long time, which is 2 millionths of a second, they will decay to give you electrons and a couple of other neutrinos, okay? So you've got something that I would call fast, which is 26 nanoseconds, 26 times 10 to the minus 9 of a second, and something that's appallingly slow, 2 microseconds. That's actually in the game, that's a long time. Just come to terms with that, okay? So we start with the pions, but the muons are what's left over. Right. So the pions, we call them strongly interacting. Indeed, they're the glue that holds the nucleus together in a real way. They're the propagators of the strong force, if you like. In other words, the glue. They produce the muons, and the muons are different because the pions interact very, very quickly, but the muons don't interact with nuclei particularly at all, not with a nuclear interaction. They're like electrons. All they ever do, really, I know it's technically not quite right, but we're doing okay here. They act like massive electrons. Their mass is about 200 times the mass of an electron, their rest mass, okay? And they don't have strong nuclear interactions, which means that all they interact with is their electric field. They've got charges, and so as they go through material, those charges will interact with electrons in the material. They might knock the electrons out of various atoms. And so we'll say that they ionize the atoms as they go through. Muons, like electrons, are basically relatively straightforward compared to the other things that go on in the nucleus, but we don't understand everything about them still. We don't really understand their magnetic moment, for instance, not properly, but basically we understand a lot of those things, and the same with the electrons. We understand most things about electrons, but not quite everything. But the muons and the electrons are sort of okay. Are we doing okay so far, Mike? Oh, okay, thanks. Okay, so we've got these particles that are coming down through the Earth's atmosphere. Many of them are produced, as I said, 20 kilometers up in the atmosphere, something like that. It's called the Pfotzer maximum if you want to have a look it up, PFTOZER or something like that. And these things come down through the atmosphere. When they come down, they're continuously losing energy because they're continuously ionizing material in the atmosphere or whatever material they go through. But this isn't a very rapid energy loss mechanism. In the particle physics game, we say that they lose 2 MeV per gram per square centimeter. Now, I said that quickly just to confuse you, okay? An electron volt is just a measure of energy. An MeV is 1,000,000 electron volts. It's not a lot of energy in this scheme of things because these muons that we have that reach sea level have typically got energies of 10 to 50 GeV. So that's 10 to the 50,000 electron volt, 1,000 million electron volts. And so these are 2 MeV per gram per square centimeter is not much, but it's a bit. They lose some energy. Otherwise, we wouldn't be able to detect them. We detect them by seeing the effect of, as I mentioned, of their electric field interacting with scintillator or with other materials that they go through. Okay. Okay. Right. Where do they come from? I'm going to talk to you a little bit about that, and then we'll come back. These cosmic rays in space are energetic nuclei. They've come from great distances. If I measure particles in the heliosphere, they've come relatively locally. They've wandered around for 1,000,000 years or so. But if I measure things with our Pierre Auger Observatory, which we built in Argentina, they've traveled for 300 million years or something like that. They've traveled a long way through the universe. So these things are interesting from an astrophysical point of view. So, but the muons that we study here, mainly the 1 per square centimeter per minute, are produced around 20 kilometers altitude, and many of them reach ground level, 100 particles a second going through your body. Fine. Uh, the lower energy ones have come in through the heliosphere. That's the region around the sun. The sun has a solar wind which blows out. It's got charged particles in it. It's a plasma. And so particles that come in through the heliosphere have to fight their way in through that solar wind. And when they do that, if the sun's very active, you get less of them because the solar wind's stronger. If the sun's less active, you get more. So you get as a plot at the top here, you get a variation which is quite measurable of the number of particles that's coming over a daily basis. The data that's shown there is about a month's worth of data, and you can see it varies a reasonable amount. And the picture at the bottom is just one of the things that happens with the sun on a daily or weekly basis. Just at the moment, we're running through what's called a co-rotating interaction region, which you don't want to know about, but it's just the solar wind that's affected a bit, and that affects the number of particles that we measure. So my personal interest is measuring this variation to try and figure out if the sun works. Okay. I shan't bore you more with that unless you ask me a question about it. Okay. Need to talk about a bit of physics. Our atmosphere, if you measure air pressure, you used to measure air pressure with a barometer, and it used to be 760 millimeters of mercury. And people would have a tube which had mercury in it, wonderful stuff. And that would be about 3/4 of a meter high. And the height of that tube would go up and down a little bit because it was supported by the atmospheric pressure, and you could measure atmospheric pressure with that. Now, 760 millimeters of mercury is about equivalent to the same mass as 10 meters of water. So what holds that barometric tube up is just the mass of the atmosphere above the barometer. And so our atmosphere has got a mass above you, just the same as if you were under 10 meters of water. So if we now think about 10 meters of water, because that's easier, if you take 1 square centimeter of it and you think of how much stuff there is above a square centimeter, I'm pretty sure you would get 100 grams of water above there. So I would say, in my jargon, there's 100 grams per square centimeter of atmospheric absorber above us, because water's got a density of 1 gram per cubic centimeter. Okay, just think about that. But from my point of view, as having something as an absorber, our atmosphere is worth 1,000 grams per square centimeter. Fortunately, that's about the same number as the number of hectopascals. And so I tend to mix up hectopascals and grams per square centimeter, both about 1,000. Now, if you look up the particle physics handbooks, you'll find that many particles will interact with material in terms of the number of grams per square centimeter. It doesn't matter too much what the material is usually, unless you've got a really massive nucleus, lead or something like that. But basically, the number of grams per square centimeter just tells you how many electrons there are per square centimeter, because the grams really just go with the number of protons. Neutrons are about the same numbers. So it just measures the number of electrons that your particle is going to interact with. So, which means that you can have 1,000 grams of mercury, 760 millimeters, or 1,000 grams of water, 10 meters, or 88 centimeters of lead. And for a lot of absorption, particle absorption, you get the same amount of absorption because you got the same amount of electrons there. Come to terms with that. It takes all of us a little while to really believe that our atmosphere is just worth 10 meters of water. but that's just basic physics, just pressure. Okay. So muons in the atmosphere got a huge range of energies, but most of them have got typical energies at sea level of, as I said, 10 to 50 GeV, 10 to 50 billion electron volts. And 2 MeV per gram per square centimeter isn't too much because our atmosphere is 1,000 grams per square centimeter. So even going through the whole of the atmosphere, you just lose 2,000 MeV, 2 GeV, and I just told you that their original energies were maybe 10 to 50 GeV. So you lose a bit, but not too much. Okay, there we go. So these muons will quite cheerfully come through that amount of material. But, and the but is, what worried people when muons were first discovered is that you could measure the lifetime of these things. And the lifetime is 2.2 millionths of a second. Now, the speed of light is a nanosecond per foot. See, God used proper units. Nanosecond per foot is convenient, or 3 nanoseconds a meter. And so at a speed of 3 by 10 to the 8th meters per second, for 2 millionths of a second, you'll travel 660 meters. These things, these muons, will decay in 660 meters, but I've just told you that they've come from a height of 20, 30, 40 kilometers in the atmosphere. And in the 1930s, people realized that it was possible for this to work if you had special relativity. That is, if the time that you were viewing the muon for was dilated from 2.2 millionths of a second to a time that was a lot bigger, then in fact the muons could get to us. And so by time dilation, it's possible for the muons to actually reach us. And there was a guy called Bruno Rossi in 1941 who went up a mountain in the US, Mount Washington, I think, if I remember rightly, and measured the number of muons at the top, measured the number of muons at the bottom, and found that everything worked perfectly well so long as special relativity worked. Now, if you're not familiar with special relativity, there's a factor called gamma in special relativity, which is the ratio of the actual total energy of something to the mass energy that a particle would have if it was just sitting there doing nothing. So the mass energy of a muon is around 100 MeV over c squared. Got to get the c squared in there, and its energy is tens of GeV, which means that the gamma factor, which is tens of GeV divided by 100 MeV, is 100 or 1,000. It's a big number, which means that the lifetime of the muon for us as an observer is increased by that factor, hundreds or thousands. So instead of it being 2 millionths of a second from our perspective, then it's actually plenty to get through the atmosphere. Okay. So you asked the awkward question, what does the muon think is happening? And the awkward thing, and the thing that the muon is seeing is that the distance is shortened. And the distance is shortened by the same amount. So the muon thinks, oh, I can just live for 2.2 millionths of a second, but I've only got to go through 100 meters or so of atmosphere because I've got length contraction from my point of view. So you've got to get the points of view right, okay? So it works, and so special relativity was proved by Bruno Rossi and a guy called Hall, who I don't know about, probably a student, probably, in 1941. Okay. Now, the wonderful people at Swinburne Uni I helped them They call me a scientific advisor. I'm not sure why, but they don't pay me particularly for it. So I'm not trying to sell this, but I would like to show you this thing called EduMOD because they loan one to me, and it's beautifully made. I mean, I wouldn't say it was. I've made a lot of muon detectors in my time, none of them nearly as nice as this. So EduMOD consists of two plastic scintillators, like the ones that I showed you, and they're square, and you can see them in the picture here, one above the other. So if a muon goes through, the signal, you get a little bit of light in each plastic scintillator. That little bit of light is picked up by a number of silicon photomultipliers that are attached to the side of the scintillator, and you get a signal. If you get a signal through both of them, it means the muon has gone right through. So it's not just a bit of radioactivity, a bit of alpha particle that just interacted with one of them. And that signal goes to the nice red, orangey sort of box. And that decides if there's been a signal in each of the scintillators. Yeah, do that. If it has, then EduMOD records that. It records that to around a millisecond. And so you can measure your muons arrival times to a millisecond with this. It's really user-friendly. Even I can use it. I just stick a laptop on it and it's wonderful. It just works. And that's saying something because most things that I build take a while to work. Okay. All right. So these things, you can separate them. You make a little directional telescope with them. And if you point that directional telescope in a direction away from the zenith, you get fewer particles there. And so you can measure what I would call the zenith angle distribution. And that varies roughly as the square of the cosine of the angle from the zenith. If relativity didn't work, you would get none away from the zenith because you're looking through more and more atmosphere. You're looking through larger and larger distances. And you'd actually check that relativity works right with a bit of knowledge about the energies of the muons by pointing this thing in different directions. Alternatively, you can do what Rossi did. You can take EduMOD because it's portable, because it just runs off a laptop. You measure the rate of muons at the bottom of a hill, measure it at the top, and you can do Rossi's experiment, which was incredibly difficult in 1941, which is really easy with EduMOD. And I should say that all the experiments that I describe here, I've done myself because I was sort of interested. Okay. Muons go through stuff and they do lose energy. So if you want to look through something, X-ray something with muons, you can do it. And famously, this was first done by a guy called Louis Alvarez in the 1950s, I think, looking for chambers in pyramids in Egypt. And that's continued to be done. And just a couple of years ago, some people at University of Nagoya in Japan found a new chamber in one of the pyramids by measuring the muons coming through in various directions. And they found there were a few directions where more muons came through than they expected. And so they could do muon tomography. Now, other people wanted to do muon tomography also. People who want to check that trucks aren't bringing uranium when they shouldn't be also like to do muon tomography. But I keep telling them it doesn't work very well, but they keep trying. Okay. So you can measure the absorption in a building. If you've got a high building, you can measure the rate of muons at various floors in the building and figure out how much absorption you get in each of the floors. You get an exponential absorption there. Again, our Japanese friends use muon tomography to measure volcanoes. It's awkward to actually wander into a volcano and make measurements within the volcano. But if you measure the muons coming through the volcano, you can figure out what's going on inside the volcano, and that's what can be done. And our friends at Swinburne University have made measurements at tailing dams of mineral sites in South Australia and down mines elsewhere, again using muon tomography to check that things are working right. Okay, right. So let me just summarize a little bit of what I've said. They were discovered by accident by early people using, in particular, cloud chambers. Cloud chambers used to be, you used to have a cloud chamber and you used to just fire it off, and you used to measure nothing in particular. And until a guy called Patrick Blackett came along, and he had a guy who worked with him called Charlie Wynne Williams. And Charlie devised a way of having a Geiger counter underneath the cloud chamber, which then triggered the cloud chamber. So you had a very efficient cloud chamber then, because you always knew that you were going to get a picture of something. This was actually, Charlie then had to design an electronic circuit for this, and that circuit was a monostable multivibrator. For people in the electronics business, you would know that that's the basic circuit for computers. And in fact, Charlie went on to work at Bletchley Park, even though none of us knew it later on, with a guy called Turing, and built the first computer. I say that because pure scientific research, you say, that's just a waste of money. But in fact, you wouldn't have computers if it wasn't for people in this game. So I thought I'd put in a plug. Okay, all right. So there are always spin-offs. If you try to do something really difficult, you learn to do something really hard, it becomes useful. I wanted to just end by giving you a little bit of a list of things that if you got EduMOD, or there are other people who make muon detectors as well, but I've really enjoyed using EduMOD. Nobody tells me to say that, but I have. So what can you do? And I've done all of these things. You can take EduMOD up a hill, and in Adelaide behind us, we've got Mount Lofty, which is 800 meters almost high above Adelaide. And you can measure the difference in the rate of muons from up there. That's the experiment that Rossi did. And I wrote a little document that tells you how to do that. You can also measure, as I mentioned, the rate of muons as a function of zenith angle, this cos squared theta thing, which again requires relativity, special relativity to understand it. Secondly, the muons come randomly. That means that if you measure the time between their arrivals, and you can do that with EduMOD because these are timed to millisecond accuracy, then you get an exponential distribution. And the exponent of the exponential is actually the mean rate that you have. And you can then study statistics, what are called Poisson statistics, if you want to teach that or want to understand that. And this is the same statistics that you get if you want to figure out how many gates to open on the Sydney Harbour Bridge because cars come in randomly, or if you want to understand how people are going to vote, if you have a survey of voters, the uncertainty in that is just Poisson statistics. So you can relate counting statistics to many different environments. You can do simple building tomography. As I mentioned, you can measure the rate of particles at different heights, different levels in a building to look at the absorption in the building. You can do that on a small scale, which we've tried by putting buckets of sand on top of the EduMOD detectors, and you can measure the number of grams per square centimeter and see that if you replace a bucket of sand with a bucket of water or some steel plates, then you get the same absorption for the same number of grams per square centimeter. And that's core business for everyone in the particle physics business. If you measure the muon rate, 100 particles per second, you can figure out a radiation dose. And that enables you to talk to students about radiation doses in general and talk about radiation doses, for instance, in aircraft. Now, if you're interested in that, there's a website called Sievert, Sievert, which will tell you what your radiation dose was for any given flight that you happen to be on. You can look it up and they'll tell you how many rads of radiation you've had on that. So that's a nice thing to discuss as an extension with students. If you separate the two EduMOD detectors horizontally, you're actually measuring, if you remember looking back at the cloud chamber picture, you saw a very central core of particles. If you're separating the particles horizontally, means that you measure the same cascade of particles and measure how wide that is. This is called a decoherence curve, and it's not too fashionable as research now, although I've done it, but it's a really nice thing to do in a school. The final thing that you can do, of course, is just measure the rate of muons as a function of time, and then you can measure things about the sun, the heliosphere, and the like. So that's just one further thing that you can do. Okay. So I'm not sure. I've probably run way over time. I'm not sure, but thank you for listening. Matt may have some questions for me. I'm not sure, but I'm happy to take questions. Or if you've got questions and you just send them to Matt later, I'm happy to have them sent on to me and attempt to answer them for you.
Thank you so much, Roger. I really enjoyed that. And if anyone does have a question, feel free to put it in the chat now, and then I'll just organize the questions as they come through. So as I said, feel free to put your questions in the chat there.
Or if Matt thought there were things that I said that were totally obscure and unreasonable, that's I can talk about them also.
So Sam has a question in the chat. Sam, could you please, Samuel, unmute yourself and yeah, feel free to go for that question if you like. I'll just see if Samuel can unmute. If not, I can repeat this question. It's just the question, Roger, is
Yeah,
you mentioned a document for observing the difference in muon count that
yeah.
we could do in schools. Could that be made available as well?
Um, I Of course it can. And the people at Swinburne have been collecting these that I've been writing for them. So maybe Matt, you can talk to the Swinburne people. I'm not sure what the status of that is from their point of view, but I've written rough drafts of probably 8 or 9 things that you can do with EduMOD.
Yep.
And I'm not sure if they're going to put that into a total document or what, but it exists. If you can't get that directly from the Swinburne people, which would be the right way to do it, I think, then just if Matt would let me know, then I'll get that document for you. Anyway.
Excellent. Yes. No, thank you. And I'll just add to that. Samuel, I've used this with students, and the application that I used was the students collecting the data for a 20-minute period and then analyzing that data. One experiment that I did recently, actually, with Pepper from MDetect was at a physics teachers conference in Melbourne. We set up the detector and changed the angle of the detector by 10 degrees and did 5 minutes of data collection per 10 degrees and then plotted that curve. And then that worked very well because, as Roger said earlier, it's not a cos relationship, it's a cos squared relationship. So that was pretty cool as well. Kathy, if you'd like to, oh, yes. So I'll just read a little bit of Kathy's question, which is, or comment. Happy Pi Day, everyone. Happy Pi Day to everyone as well. Thank you, Kathy. What amount of height would you need to get a significant difference in muon count? We don't have a mountain nearby, but there's a bit of a hill. That's a good question. Would you?
Um,
Yep.
I uh, Anything you like and it will work, but uh, since the count rate is fairly modest, then you're stuck with counting statistics. So
Mm,
let me just comment that if you count random things like muons, uh, then the uncertainty in the count is the square root of the number of counts, called Poisson statistics. And so if you were to measure a relatively short height, you have to count for longer to reduce that counting uncertainty sufficiently that you can see the difference. So I've done that in the building that I'm in here, which has got 6 floors in it. I've been on the ground floor and I've done it on the top, uh, and I can do it, but I have to count for quite a long time to get the statistics short enough. Now, when I went up Mount Lofty, which is 750, 800 meters high, then I could do that in 5 minutes to get enough counts there and enough counts down here. If you go to 1/10 of that, you're probably going to need 3 or 4 hours to get the difference, simply because you've got to have enough counts to measure that small difference in rate. So you could do it, but you wouldn't do it in a classroom period. You'd do
mm.
it overnight or something like that.
Yep.
Yeah.
And another question from Penny is there a size limit for the muon tomography?
Sorry, is there
A size limit. So Penny, if you want to extend upon that question at all, feel
yeah,
free to do in the chat.
a size limit of what you're measuring the tomography of, or a size limit of your detector, or I wasn't sure just what you were getting at
Yeah,
there.
sure. I'll let Penny comment on that in the chat in a moment. Um,
Okay.
oh, so talking about, you mentioned it was not effective for something, but good for pyramids. What's that? Oh, not effective for trucks. Um,
Yeah, because people don't want a truck to be hanging around for a quarter of an hour while somebody measures what's going through it.
yes.
That's all. But one thing, I don't know if Matt did this, but certainly I've done it in my office here. My office has got a window on one side and it's got the rest of the building on the other side. If you do what Matt did, which is to measure the rate at some angle from the zenith, and you point that through a fairly thin wall, and then you swing everything around 180 degrees and point it through the mass of the building, then you get a change in rate from that, which is not too difficult to measure. Again, probably not very easily in a single classroom period, but you could do it as a project relatively easy over a couple of hours, for instance.
And to just comment on the height difference, as Roger said, the greater the height that you do, the better. If you live obviously somewhere in Sydney, there is the Blue Mountains, which goes over 1,000 meters in elevation, which is quite nice. There was a teacher from North Sydney who went on a couple's getaway and took the muon detector to the top of the Blue Mountains. So her husband drove, and she had the laptop and the muon detector in the footwell, collecting data all the way up. I'll just share
I
my.
hope the husband appreciated that.
Oh, that's it. Very, very romantic. And then I'm going to just quickly share my screen for one moment. I just want to show everyone this. This is an extreme example of changing your altitude. So this was the muon rate count per 30 seconds going from Melbourne to Brisbane on a flight. So I had the muon detector with me and I started detecting on the tarmac before we took off. The plane took off, and then we're at altitude, 33,000 feet or 10 kilometers in elevation. And you can see the muon rate count skyrockets, and that was pretty impressive to watch that on my laptop. And then the plane descends, and then we land in Brisbane. Um, so that was pretty cool as well. So that's a big change in altitude. Instead of obviously 1 kilometer, it's 10 kilometers in altitude.
Yeah, so Matt and everybody, that's you can see the reason why cabin crew and pilots have a fairly substantial radiation dose. For instance, I don't know if it's still true, but Lufthansa wouldn't have women as cabin crew who were at an age at which they might have children. So it's a serious issue. Uh, and you can extend the discussion to radiation in space, and then ask your students if you're going to have 6 months going to Mars and you're going to set up a colony there, who's going to have children? And the answer is you're not.
Mm. Yeah. Yeah, that's exactly right. Going to Mars, you're not shielded for the whole trip there.
Yeah, you've got a few millimeters of aluminium all around you.
Yeah.
Otherwise, it's too massive to take off.
Mm. I'm just checking if there's any questions in the chat. I can't see any more for the moment. I will let you know that actually, there is. Awesome. Oh, that's just a comment from Linda saying thank you. I'll just let you know that you can purchase these detectors, or you can rent one. And I'm running a Muon course where I send you a detector and I teach you how to use it. You set it up, and I'll just put the link in the chat. Let me just do this. This is the next edition of the course, and you get to keep the detector for 2 weeks afterwards. So after you learn how the detector works and do all the statistical analysis with the data, you can then use it for the 2 weeks afterwards with your students. So that workshop is this term, but there'll also be a few more workshops next term. So if you'd like to express interest in that, I'll just put my email again in the chat there. And so you can flick me an email so I can let you know when the next workshop is. There we go. I just put that email there. So it is pretty cool. As I said, I send you the detector. You get to build it and use it. Learn how to do the statistical analysis. You can also plug the detectors into an oscilloscope, which is beautiful to see the trace and capture a muon event, which is where you get to see a line or a positive detection in both plates, in both the upper and the lower plate. And so you can see that on the oscilloscope. Any other comments in the chat there? I'll just check with everyone before we sort of wrap up.
Matt, if you're actually doing that, then stick some absorber between the two, and you'll find that the top one gets the more muons than the bottom one does.
Mm. I know. Now I feel like I need to go shopping for some lead plates.
Oh, not in schools.
Yeah, no. Just me at home in my office here. Yep.
Yeah.
Awesome. If no one's got any questions, we might wrap it up in a moment. Thank you all for joining, and a very special thank you to Roger for joining us and sharing your knowledge with us. Really appreciate you doing that. And there's already been a request for your slides, which is great. And as you know, this Zoom is being recorded, so I'll end recording and I'll save this and give you access to that. So if you want to use it with your students. One last thing that I was going to mention, I just wanted to note this is. There's a few videos out there for muon physics, and I'm just going to see if I can access my favorite one, and I'll put it in the chat. You may have seen it. It is on Mount Washington. It's the Fritsch and Smith experiment, and we go. The video is quite long, but I think it is amazing in the depth it goes into. It's 35 minutes long, and I'll just put it in the chat. Some of you may have seen it before. I'll just put it in the chat there. But it's a great video. Just give me a little wave if you've seen that video there, the original. Paul's seen it. Nice, awesome, cool. All right, well, I think we might finish up there. Thank you so much for joining me on a Friday afternoon. I hope you have a great weekend. And on behalf of everyone, I'd like to thank you, Roger, for your Friday Arvo and sharing your knowledge.
And thank everyone from me for coming and listening.
Thank you, Roger. If you
Okay.
have any questions, I'll stick around. Roger will stick around, but otherwise, have a great weekend.